Hello everybody and welcome to another Perspective video, where today we will be doing the GCSE Physics AQA Paper 1, and in particular we're going to be doing the 2023 paper. And without any further ado, let's jump straight in. Now, Figure 1 shows how the national grid connects a power station to consumers, and we just have to complete these two sentences. Transformer X causes the potential difference to increase, and Transformer X causes the current to decrease. And that's because, as it goes over these transmission cables, you want the least amount of energy loss as possible. So, to do that, you need the current to be really low, so less energy is lost to the surroundings. So what happens is that the potential difference increases. And because P equals IV, because the power is constant, for the potential difference to increase, the current must decrease. So the potential difference increasing, the current decreases, and all this allows the energy to be carried over transmission cables at a higher efficiency. And in other questions, this is usually called transformer Y, and this does the opposite. This causes the potential difference to decrease and the current to increase, so it's safe for consumers. And then we're asked what equation links the current, the power, and the resistance. We have the formula booklet as it says, so we can just look in that and see that P equals I squared R. And then for 1.3, it's just a maths equation. A transmission cable has a power loss of 1.6 times 10 to the 9 watts. The current in the cable is 2000 amps, and we just need to calculate the resistance. Well, P equals I squared R. So 1.6 times 10 to the 9. Put that. Equals 2000 squared times R. So it's just 1.6 times 10 to the 9 over 2000 squared, and that gets you an answer of 400 ohms. And then once again, we're just asked to use the physics equation sheet to give the equation which links efficiency, total energy input, and useful energy output. Efficiency equals useful energy output over total energy input, and then we have this here. The national grid has an efficiency of 0.992, and the total energy input is 34.2 gigajoules. Well, it wants it in gigajoules. So what we simply do is simply just rearrange it to get a useful energy output, and we get 33.9 gigajoules. And not that it matters for this question, but a gigajoule is also times 10 to the 9. So it goes kilo, which is times 10 to the 3, mega, which is times 10 to the 6, giga, which is times 10 to the 9, and tera, which is times 10 to the 12, and that's all you need to know for GCSE Physics. And then moving on to question 2. Figure 2 shows the equipment a student used to determine the specific heat capacity of iron. The iron block the student used has 2 holes, one for the heater and one for the thermometer. Before the power supply was switched on, the thermometer was used to measure the temperature of the iron block. The student left the thermometer in the iron block for a few minutes before recording the initial temperature, and we're just asked to suggest why. And that is for the thermometer to get like acclimatized to the iron block. So the student left the thermometer in the iron block so that the thermometer temperature was the same as the temperature of the iron block. And then for question 2, figure 3 shows how the temperature changed after the power supply was switched on. The energy transferred to the iron block between 5 and 10 minutes, which is these points, was 26,000 joules. The mass of the iron block was 2 kilograms. Calculate the specific heat capacity of iron. Well, what we need here is the change in temperature. So the temperature starts at 28 and ends at 54. So temperature change is 28. 54 minus 28 equals 26. It's just that. And then we simply use the physics equation sheet. Energy equals specific heat capacity times mass times change in temperature. 26,000 equals 2 times 20 equals 2 times C, which is the specific heat capacity, times 26. You don't really need to do all this. You can just do some simple mental maths, work out that C is 200 joules per kilogram Celsius. And then the student repeated the investigation but wrapped insulation around the iron block. What effect will adding insulation have had on the investigation? Well, that's because the specific heat capacity will be more accurate, and that is because the iron block will transfer energy to the surroundings at a lower rate. So basically, less energy is lost to the surroundings, so more energy is actually spent up heating the iron block, which means that the energy calculation we're using here, the 26,000 joules, will be more accurate to the actual energy that is used in heating up the iron block. Okay. Then for question 3, figure 4 shows an electrical circuit used to heat the windscreen of a car. Each resistor in the circuit represents a heating element. The 12-volt battery supplies direct potential difference. What is meant by direct potential difference? The polarity of the potential difference does not change, and the current always flows in the same direction. So for like alternating current, it just alternates at a frequency. The polarity changes every it's usually like every 50 or 60 times a second. But for direct potential difference and direct current, it always flows in the same direction. Flow of charge is always the same polarity. And then we're meant to use the physics equation sheets again. They're just giving you 3 marks for these multiple choice. Which equation links charge flow, energy, and potential difference? And that is that energy was charge flow times the potential difference. And then we're meant to calculate the charge flow through the 12-volt battery when it transfers 5,010 joules of energy. Well, energy equals voltage times charge flow. So 5,010 equals Q times 12. Q equals 5,010 divided by 12, and we get a charge flow of 417.5 coulombs. And then ice forms on the windscreen at a temperature of 0 degrees Celsius. The electrical circuit transfers 5,010 joules of energy to the ice, and a mass of 0.015 kilograms of ice melts. We're meant to calculate the specific latent heat of fusion of water, and we're meant to use the physics equation sheet. So once again, it's just plugging into the formula we get from the equation sheet. Energy equals mass times latent heat of fusion. We then simply just plug the numbers in and rearrange, and we get a specific latent heat of fusion of water being 334,000 joules per kilogram. And then the electrical circuit was left switched on while the ice changed from solid to a liquid and increased in temperature 5 degrees Celsius. Explain the changes in the temperature and movement of the particles as the ice melted and the temperature increased to 5 degrees Celsius. Well, in the solid, the particles are arranged in a regular pattern and vibrated around fixed positions, while in the liquid, the particles are in a random order and move freely. As the ice changes to water, the temperature remains constant because the energy supplied increases the potential energy of the particles rather than the kinetic energy. And then sort of inversely, as the water warms from 0 to 5 degrees, the particles move faster, so the kinetic energy of the particles increases instead of the potential energy. And then the internal energy of the substance is the total kinetic and potential energy of all the particles. So like the overall internal energy increases throughout the process no matter whether it's change state or temperature. This part, which is like worth 2 or 3 marks, is just basic Key Stage 2, Key Stage 3 science. But as we move into the later half, we get into the specific GCSE content. Then moving on to question 4. A remote village in the UK, aka where I live, it's so annoying living in that village, uses a hydroelectric generator to provide electricity. In one day, 2.5 million kilograms of water passes through the hydroelectric generator. The change in the gravitational potential energy of the water is 367.5 megajoules, and the gravitational field strength is 9.8. And then we're meant to calculate the mean change in height of the water as it moves through the hydroelectric generator, and we're meant to use the physics equation sheet. Well, as I said earlier in the video, a mega anything is times 10 to the 6 of it. So we simply times 367.5 times 10 to the power 6 to get 367,500,000 joules. And then we just plug into the physics equation sheet formula. Gravitational potential energy equals mass times gravitational field strength times change in height, and then we simply divide both sides by 2.5 million times 9.8 to get the height of 15 meters. For stuff like this, if you get a nice answer like this, like if you get a whole answer, it usually means you got it correct. It does. If you get an unwhole answer, it doesn't mean you're necessarily incorrect, but it's a good thing to know you're on the right track. It's a good way to know you're on the right track. And then for 4.2, the generator transfers 3 kilowatts of electrical power, and we're meant to calculate the time taken for the generator transfer 2.16 times 10 to the 7 joules of energy, and we're meant to use the physics equation sheet. Once again, some simple unit conversion. 3 kilowatts is 3000 watts. Then we simply use the power equals energy over time formula and just rearrange to get time, plug the numbers in, and we get 7.2 times 10 to the 3 seconds. And it wants it in standard form, so you need to know a bit of standard form because your calculator wouldn't give 7,200 in standard form, but that's a fairly easy conversion. Figure 5 shows how the power output of the generator varied during 1 year. A solar system is installed in the remote village in addition to the hydroelectric generator, explaining why this improves the reliability of the electrical supply to the village. Well, in the summer, the power output from the hydroelectric generator is lower, but the solar power output would be greater during the summer. So there is less variation in total power output, which improves the reliability of the electric supply. So for like, you'd expect the solar power output to look something like this. So it ends up sort of providing a constant output throughout the year of like that, if you add them together. And then for question 5, some isotopes emit nuclear radiation. Carbon-14 and carbon-12 are isotopes of carbon. Compare the structure of an atom of carbon-14 with the structure of an atom of carbon-12. Well, both have the same amount of protons, so they have the same atomic number, and both have the same amount of electrons. The difference is that carbon-14 has 8 neutrons, and carbon-12 has 6 neutrons, and you can simply do that by minusing the proton number of 6 from these two numbers. So they have different number of neutrons, and therefore they have different mass numbers. And then moving on to 5.2, carbon-14 is a radioactive isotope. Carbon-14 has a half-life of 5,700 years. What does a half-life of 5,700 years mean? The half-life of 5,700 years means the time it takes for the number of carbon-14 nuclei in a sample to halve is 5,700 years. And then table 1 gives the half-life of some other radioactive isotopes. A sample of fluorine-17 has an activity that is 1/4 of its original activity. And we're meant to calculate the age of the sample of fluorine-17. Well, the activity is 1/4, so that means 2 half-lives have passed because it's half to a half, and then it's half, that half has halved again to a quarter. So we simply multiply this age by 2 to get, that is fluorine-18, we simply multiply this age by 2 to get an answer of 128.74 seconds. That's why it's important to check your work in. This is my job, or not the YouTube tutoring, and I still made a silly mistake. And then moving on to 7.4, all of the isotopes in table 1 emit beta radiation. Explain which isotope would cause the biggest risk to a person's health based only on the half-life of each isotope. Well, we're looking at the half-lives. Nitrogen-18 has the shortest one, which means it's decaying the fastest, and is therefore also emitting radiation the fastest. So, nitrogen-18 would cause the biggest risk to health. Nitrogen-18 has the shortest half-life, so it has the greatest activity, meaning it emits the most radiation per second. Therefore, a person exposed to nitrogen-18 would be exposed to, and therefore absorb, the greatest dose of radiation per second. People who work in the nuclear power industry need to be aware of radiation and contamination, and we're asked to describe the difference. Irradiation is the exposure of an object or person to radiation from an external source. Contamination is the unwanted presence of radioactive material on or inside a question. So radiation is if I shoot you with a cancer ray. Contamination is if you eat said cancer ray. This is a fairly nice question. Usually it's stuff like, why would they want to wear gloves while handling radioactive material? And then it provides a small thing saying the gloves do not provide protection from radiation. So like, you don't want to get the radioactive material actually on your skin. So what happens is if it gets on the gloves, you throw the gloves out and the contamination goes away. Even if the gloves won't actually stop any radiation from reaching your skin. And then we're asked to give one health risk to a person working close to a source of nuclear radiation. I wrote cancer/tumors. I probably should have just stuck to one because it says with one health risk. But yeah. And then for 5.7, workers in nuclear power stations are monitored to check the radiation they emit. A worker stands 1 centimeter away from a radiation detector. The amount of radiation the worker emits is recorded. Explain why the worker needs to stand close to the radiation detector. Well, some radioactive materials emit alpha radiation, which has a very short range in air. So the worker must stand close so that the alpha radiation can reach the detector. Because if they were standing like greater than 5 centimeters away, the alpha radiation wouldn't reach the detector, so it wouldn't be measured. Workers in the nuclear power industry are exposed to nuclear radiation. Pilots on aircrafts are exposed to cosmic radiation from space. The daily dose caused by working in the nuclear power station is 0.00050 millisieverts, and hourly dose from cosmic rays to a pilot while flying is 0.003 millisieverts. Calculate the number of days it takes for a nuclear power station worker to receive the same dose as a pilot flying for 24 hours. Well, a pilot's dose in 24 hours is just this times 24 hours, getting a 0.072 millisieverts, and the number of days equals the pilot's dose divided by the daily worker's dose. So the pilot's dose in 24 hours, as I said, is that, divided by the daily dose caused by working in a nuclear power station, which is 0.00050, and we get the number of days being 144. You don't actually need to really know what millisieverts are. It's just the unit used to measure radiation exposure. Because it's a ratio, you can work it out even if you don't know what millisieverts are. So don't just automatically rush to the physics equation sheet for every single math question. It won't always be necessary, and they'll usually say when it is. And now moving on to question 6, a student investigates how the current in a filament lamp changes. And now moving on to question 6, a student investigates how the current in a filament lamp varies with the potential difference across said filament lamp, and figure 6 shows the results. And then we went to describe a method the student could use to obtain these results, and we should include a circuit diagram. Well, firstly, we just have a small description of the actual circuit diagram, and what it is it is a simple power supply, and it's connected in, there's an ammeter in series with the filament lamp and variable resistor. So let me just draw all that. And then there's a voltmeter in parallel with the filament lamp. And then what we do is we use the variable resistor to adjust the current in the circuit. And then we record the set current from the ammeter and potential difference from the voltmeter, and we vary the potential difference from 0 to 6 volts in intervals of 1 volt. Yeah, this, a said cell, it should be a power supply or a variable power supply. Just something you can use to change the voltage. Your school probably has it, or you could use one of those power packs which you put batteries in and use varying different batteries. And then we simply reverse the connections to the power supply to obtain negative potential difference values, and we take repeat readings at each potential difference value and calculate a mean. So what this is this would be the results of the potential difference in intervals of 1 volt. We measure the current, and we simply just have a little nice graph like that. And then for question 6.2, determine the resistance of the filament lamp when the potential difference across it is plus 3 volts. Well, from figure 6, at plus 3 volts, the potential difference, no, the current is 0.16 amps. And then we simply use V equals IR, get 3 equals 0.16 times R, and just rearrange for R, getting a value of 18.75. And then there's another question. The current in the lamp is 0.21 amps when the potential difference across the lamp is 6 volts, and we're meant to calculate the energy transferred by the filament lamp in 30 seconds, and we're meant to use the physics equation sheet. Well, the time is 30 times 60, because 30 minutes, we want it in seconds, it's 1800 seconds. Then we use the formula Q equals IT, getting the charge flow to be 0.12, which is the current, times the time in seconds, and we get a charge flow of 378 coulombs. And then we simply use the E equals QV formula, getting the energy being 2,268 joules after we plug in the calculated charge flow and the voltage. And then for question 8.4, the power output for the lamp is 1 watt when the power potential difference across the lamp is 5 volts. The student predicted that the power output would be 4 watts if the potential difference was doubled. Explain why the student is not correct. Well, for the power to quadruple, both the current and potential difference would need to double. However, the current does not double when the potential difference doubles because the resistance of the filament lamp increases as the filament gets hotter. So current is not proportional to potential difference for a filament lamp. And if we go back to the figure at the beginning, we can see that it's not proportional. And if it were proportional, it would end up looking something like that. Obviously, a better diagram. Then moving on to question 7. A baby bouncer is a harness attached to a spring that hangs from a door frame. Figure 7 shows a baby in a baby bouncer in 2 positions. Position A off the ground and position B on the ground. The baby bouncer should not be used with babies that have a mass greater than 12 kilograms, and I'll suggest one reason why. Well, that's because the spring may become permanently extended or like stretched beyond its elastic limit. So basically, if the string gets pulled like too far, like if the spring gets pulled down to here, it may get permanently damaged. And then for 7.2, in positions A and B, the baby is stationary. Describe the energy transfers as the baby moves from position A to position B. Well, in position A, the baby has gravitational potential energy, and as the baby moves down, it converts to kinetic energy and then to elastic potential energy stored in the spring. And in position B, all the energy stored is elastic potential energy. So it moves from A using kinetic energy, using that gravitational potential energy to turn to kinetic energy, and then it just switches the kinetic energy back to elastic potential energy as it extends the spring. And then for 7.3, in one position, the extension of the spring is 8 centimeters. The elastic potential energy stored by the spring is 4 joules. Calculate the spring constant of the spring. Well, 8 centimeters is 0.08 meters, and then we just use the elastic potential energy formula, sub all the numbers in, and then just rearrange for K, and we get a value of K being 1,250 newtons per meter. Then moving on to question 8, scientists developed new models of the atom as new particles were discovered. Draw one line from each particle to the year it was discovered. The electron was discovered in 1895, the neutron was discovered in 1932, the proton was discovered in 1920 and the nucleus was discovered in 1911. And these are just things that you need to remember. There is no sort of, I mean, you could use the order of the models and then sort of work it out logically in what order they were discovered, but you do need to just remember the order they were discovered. The nucleus was discovered using an alpha particle scattering experiment. Alpha particles were directed at a sheet of foil. Figure 8 shows the path taken by 7 alpha particles. Explain why alpha particle A takes the path shown in figure 8. And that's because both the alpha particle, which is like, if you didn't know, it's equivalent to a helium atom, helium nucleus, and the gold nucleus both have a positive charge. And because they have the same charge, they repel each other, causing alpha particle A to be deflected back. And because both B and C weren't like going directly into it, instead of being deflected back, they're just redirected away from their straight paths. And explain why the path of alpha particle B is more tightly curved than the path of alpha particle C. And that's because particle B passes closer to the nucleus than particle C, so it experiences a stronger force from the gold nucleus, causing its path to be more curved. And then what can be deduced about the atoms from the path taken by alpha particles D, E, F, and G? Well, that's because the atom is mostly empty space. Like if there were like gold nucleuses everywhere, everything would sort of be redirected and go away. But the alpha particles, most of them going straight through unaffected, means the atom is mostly empty space. And then for question 8.5, how is the Bohr model of the atom different from the nuclear model of the atom? Well, in the Bohr model, the electrons orbit the nucleus at specific distances, or like energy levels or shells, as you may have heard of them in chemistry or other sections of physics, and not at any distance. And then we're asked to explain how an electron can move up and down between energy levels in an atom. To move to a higher energy level, an electron must absorb energy from electromagnetic radiation. And to move to a lower energy level, an electron emits energy in the form of electromagnetic radiation. Then moving on to question 9. Figure 9 shows air being pumped into a car tire, and we're asked to complete the sentence. Well, air particles in the tire move quickly in random directions. And then when the tire is at the correct pressure, pumping more air into the tire causes the pressure to increase further. The volume and temperature of the air in the tire do not change. Explain why the pressure increases as more air is pumped into the tire. Well, that's because there's more air particles in the tire, and therefore a greater number of collisions with the tire walls per second, which increases the pressure. Because pressure is just force over area, and if the volume is staying the same, the area inside the tire is staying the same, and there being more frequent collisions means there's more force. So force increases, area stays the same, increase in pressure. And then for 9.3, the air pressure in a car tire changes if the temperature of the air in the tire increases. Explain why. Well, as the temperature increases, the air particles have a greater mean kinetic energy, so they move with greater speeds on average, which means there'll be more collisions with the tire walls per second, and each collision also exerts a greater force on the tire wall because the particles have greater momentum. And the greater mean force per unit area on the walls of the tire causes the pressure inside the tire to increase. As I said, similar to the last question, greater force, same area, increased pressure. Anyway, that's the end of that paper. If you've enjoyed this video, make sure to like and subscribe, and I'll see you next time. Imagine if I didn't record that, that'd be embarrassing. Yeah.